Hello everybody, in this video, me and my boy Angel will be showing you guys how to calculate the downforce on a wing from a Ferrari 641. But before we get started, I'm going to give you guys a brief explanation on why we chose a Ferrari. Ferrari is well known for producing cars that are both stylish and really powerful. They have a great reputation in creating some of the most iconic and sought out cars. Now, before Ferrari was mainly recognized for its sports and exotic cars, they were really known in the F1 scene. Now, to be exact, one of the most iconic cars for Ferrari in the F1 scene is a Ferrari 641 from 1990. Now, this car had a Ferrari Tipo 3.5-liter V12 engine. The transmission on this Ferrari was a 7-speed semi-automatic and was pushing around 680 brake horsepower. Now let's get started with the fun part, the math, of course.
So here we have the formula for downforce for the Ferrari 641 in the 1990 season. Our first variable here is 1/2 P, which is the air density times a half. So statistically, it's 0.00119. Then we have the area of the wing, and since the Ferrari 641 has 2 wings built in, it's 11.70 feet for both wings. And then we have the coefficient of lift, and we don't really have the coefficient of lift because for that we would need to know the curve of the wing, and it's undefined because Ferrari doesn't release that publicly. They keep it private for every car, and they always have. And then we have velocity squared. So 1 mile an hour is 1.467 feet per second. And what downforce is, it's the force applied to, let's say, a wing, a wedge, or whatever is going through air, and it's the force that's pushing down or pushing up. But in this case, since it's downforce, it's pushing down. So using this equation, we have to plug in all our variables that we have. So it's 0.00119 times 11.70, which gives us 0.0139 times the coefficient of lift that we don't have, times of velocity squared. So we square velocity, and that gives us 0.0139 times 73,657.96 times the coefficient of lift. And that gives us a total of 1,023.84 times the coefficient of lift. Since we don't have that, this is as far as we got. But if we were to implement that, the readings would be about the same.